Jai Hind everyone, my name is Mukulit Goel. I am assistant professor in the department of MCA at Akgec Engineering College, Ghaziabad. And today my topic of discussion is process management and concurrency from the subject operating system with subject code BMC 203. In this topic, I will talk about the process, process control block, process states, process concurrency. So first of all, I will start with what is a process. A process is a program in execution, and it is the unit of work in a time sharing system. Like we see in an operating system, there are many processes which are executed at the same time. At the same time, we are working on the Microsoft Word. At the same time, we are listening the music. At the same time, we are taking the printout of my document. Okay, so that all those tasks which I am doing is the part of the process which is under the execution. Okay, so in operating system, there is a collection of processes like executing the system code and user processes executing user code. So the process is basically a task which is an instance of a program in execution, and this execution or process must program sequentially. At any time, at most one instance is always executing, and the current activity is represented by the value of the program counter and the content of the processor's registers. So it is the structure of process memory. Because process is known as a task or job, so it holds some memory, some space. So the process is more than a program code, which are sometimes known as a text section, and that text section is somewhere stored in our memory, and that memory must be in the form of stack or in the form of general process registers. Okay, and a process generally also includes the stack and the data and some variables which is attached to our process. So next is the difference between the process and the program. So a program by itself is not a process. When the program is in execution, then it is known as a process. Program is a passive entity, and it is the content of the file stored in a disk or somewhere in our storage. Whereas a process is an active entity with having a program counter specifying the next instruction which is need to be executed, and also have a set of associative resources which may be also shared among several processes. Like set of associative resources means कि when we are working something on Microsoft Office type application, we want to take a printout. So the resource which is associated with our process is a printer, and that printer will work when it is shared with that system, as we have installed its drivers into that system. If we take a printout from the printer whose drivers are not installed in our system, means that resource is not associated with our system. So first we need to associate the resource with our system to complete a process of writing a document and then take the output of that document from the printer. Okay. So a program is a static object where process is a dynamic object. A program resides in secondary storage while process resides in the main memory. What is the difference between secondary storage and main memory is, a program resides in secondary storage. Like I have created a document, I stored in somewhere in location in the drive C, D, E, which is already in our system. So that is the program. But the process of taking a printout is done through a resource which is attached to a program that uses some memory, and after the printout or after writing everything on the Word, when we close that Word application, the main memory swaps it data and free himself, main memory free himself, and give that address to some another process. Okay. So the span of time program is limited, while the span time of a process is limited, as when all the printout are already taken, the process is complete, the memory is free, and the another process can take place. A program is an algorithm expressed in programming language, while process is expressed in assembly language or machine language. Next, there are the 5 type of stated in process which we call as process state. So, a process have to go through these 5 states. First state is new. The first state is new, in which we commit about the process, this process is going to execute, and we have created that process. So, the creation is new, instructions execution is running. When during the execution some interrupt comes, some trap comes, some fault comes, then process goes into a waiting state. Then when from the waiting it again come to a processor, or from the new state also it comes to a state which is known as the ready state, and when we finish the execution, then it is in the terminated state. So, each process has to go through these 7 states, which is new, ready, running, waiting and terminated. And every time a process might be in any one of these 5 states till the termination. After termination, it have to start again, but after the new and till the termination, a process is in any of these 5 states. So, it is important to realize that only one process can be running on any processor at any instance, and many processors may be at the ready and waiting. So, it is the diagram of 5 states. We start with new, in which we admit a process, then that process come into a ready state. From the ready state through the scheduler dispatch, it goes into a running state. What is the scheduler dispatch? Scheduler dispatch is basically a type of the scheduler, which call it as a register, in which we schedule the processes in a queue or in a stack or in a general purpose. So, from ready that comes into the running. When during the running of the process there comes an interrupt, then again it goes to a ready state, or we are waiting for some event to occur, then from also it is running to come into the waiting, and when that event wait complete, then again it goes to a ready state. From ready state again through a scheduler dispatch it comes into a running state, and after running is completion it exit and it goes through that goes into the terminated state, means exit. So, these are the 5 states of the process. After these 5 states, there is the important thing which each operating system holds, or in operating system each process is represented through a process control block. In short form it is known as PCB. So, each process is represented in the operating system by a process control block, and it is also known as the task control block because it contains all those things associated with the process. First is the process state, means in what state the process is currently going on. Another is program counter, in which it executes or it gives the indication about the next instruction which is going to be executed. Then the CPU register, these registers vary in the number and types depending on the computer architecture, and they include accumulators, index registers, pointers, general purpose registers, plus any conditional code information along with the program counter. So, CPU register, then CPU scheduling information. CPU scheduling information means in CPU which program is scheduled and which program is going to execute it first. So, for CPU scheduling there are different types of algorithms that like first come first serve, like round robin algorithm, like shortest job first, like shortest remaining time job first. So, after scheduling information we have a memory management. How much memory is need to be stored by any process. So, this information include the values of the base and the limit registers, space tables, segment tables, and it also depends on the memory used by the operating system. Then the accounting information, this includes the amount of the CPU and the real time use with time limits. Then input output status information, what is the status of the input output devices which is allocated to the process. It is the diagram of the process control block. So we can see that the process pointer to the parent process and pointer to the process child. Then we have the process state. Then we have its process identification number. Then its priority, counters, registers, pointers to memory, memory limits, and the list of open files. So all these are the fields of the PCB, in which first we stored the process state. Then we process identification number is known as the PID. Then we have the CPU scheduling process, which process comes after the execution of this process, means what is the priority of our processes. Then after that we have the program counter. It decrements or increments depending on the processes. Registers is the part of somewhere in the memories and the stores all the address spaces. Then memory, then the memory limits and the list of open files. So here is the diagram which shows that how CPU switches from process to process. So there are two processes, which is process 0 and process 1, and first process P is going to into the execute. After execution, it is saved into the PCB of the process 0, but after the execution, it goes into the ideal state. So when it goes into the ideal state, reload process control block reloads the states of the takes the state of the process control block of process 1. Okay. So after process 1 executes, then again comes some interrupt, then save state to the PCB1. So the process control block saves the state of process 1. Then process 0's state is reloaded and it starts getting executing. So in this way, the operating system with the operating system, CPU switches between the process to process by storing their states, in which state they are going to be currently they are executing, whether they are in the new, whether they are in the ready, waiting, running and terminating. So now comes the process scheduling. Basically, scheduling is the fundamental function of operating system, because if we don't schedule, if the operating system does not schedule a process, then there is a condition comes where our system is going to be hang. And that hang system in operating systems term, we can say a deadlock type of situation, in which either we are also not going and we will also not let you to execute. Okay. So the scheduling is the fundamental function of operating system. When a computer is multi-program, it has multiple processes completed for the CPU at the same time. And if only one CPU is available, then the choice has to be made which processes need to be executed next. So this decision making process is known as the scheduling, and the part of OS that makes its choice is called as the CPU scheduling algorithms. CPU scheduling algorithms. These scheduling algorithms are the 4-5 types, which is the part of the next slide. Next my lecture. I will not discuss those algorithms here, because I discuss here process synchronization and the process management here, but I will discuss the scheduling algorithm in my next lecture. So it consists of scheduling queues. As processes enters, they are put into the job queue, and according to the job queue, all those processes which are in the system, they got executed, and after the job queue, they come into the ready queue. Okay. From the job queue, they come into the ready queue. From the ready queue, they are coming to the CPU. Then the request, which is input output request or time slice, expired. When the time slice expires, means ki what is the time which is given for any process for the execution. And if the time is that time expired, then that process will go into the waiting state, and from the waiting state, that again comes into the ready queue, and then it executes. Okay. So there might be a input output request, time slice expired, fork a child and wait for an interrupt. And when interrupt occurs, the process goes into the waiting, and from waiting it goes into the ready queue. So the ready queue and various input output device queues. We have a header of queue header. Then we have the process control blocks of the each process which is executing. The information, the address spaces, all are stored in the registers. Through those registers, we mag, tap, okay, and then we assign a disk, and we execute all these processes according to the process information or state stored in the process control block. After this, there come a schedulers. There are the three type of schedulers, which is long-term scheduler, short-term scheduler, and the middle-term scheduler. So when any event is in the new to ready state, then it is in the long-term scheduler state. And when any process is in the from the running to the termination state, then that process is in the short-term scheduler state, and from the ready to waiting and the waiting to ready, it is in the middle-term scheduler state. Okay. So the process migrates among the various scheduling queues, and these selection process is carried out by the appropriate scheduler, and these scheduler are of three types, which is long term, short term, and middle term. So as I said, the long term is between the ready new to ready, short term is between the ready to running and for the completion, and from running to ready, these states are in the middle term scheduler states. So addition of that, there is a middle term scheduling in which the process is between the running ready and the waiting state. So how it executes? There is a program is in the ready which comes in the CPU. Either it swaps out, or we are waiting for some input output operation. It goes into the queue or it goes into the ideal state. So when it goes into the ideal state, then it comes into the waiting is ideal state means waiting state, and after waiting state is over, it again comes into the ready queue, and from the ready queue, then it comes into the running queue or running state, and from that running state, then it executes and finally terminated from the process state. So when I talk about the description of all these type of schedulers, long-term scheduler select the processes from the disk and loads into the memory for the execution. It controls the degree of multiprocessing. It is a long time duration scheduler, so it is very slow. Okay, and due to the longer intervals between the execution, it cannot afford to take more time to decide which process should be selected for the execution. Next, short-term scheduler selects among the processes that are in the ready state to execute and allocates the CPU to one of them. The primary distinction between the two schedulers is the frequency of their execution, whereas the long-term scheduler is slow, short-term scheduler is fast. Okay, and it frequently executes. It must be at least 100 milliseconds in which we execute one process in the short-term scheduler. Third is the middle-term scheduler. In middle-term scheduler, operating system introduces the additional intermediate level of scheduling. The main idea behind the scheduler is that sometimes it advantageous to remove process from the memory, thus reduce the degree of multiprogramming. We free the memory, but we will not free the process queue from the execution of that process. So that process that is known as swapping. So we swap into the memory and we swap out from the memory during the middle term scheduler, as I also shown in the diagram here. Swap out and swap in. So it is the short differences or similarities between all these type of schedulers on the basis of their aspect. So in their aspect, there are the 5 aspects which is they are known as, according to their speed, their level of multiprogramming, their time sharing system, and their processes. So long term scheduler is a job scheduler, middle term scheduler is a process swapping, and the short term scheduler is the CPU scheduler. In terms of speed, long term scheduler is slow, short term scheduler is fast, and middle term scheduler's speed is between the long term and middle term scheduler. Long term scheduler controls the degree of multiprogramming, middle term scheduler reduces the degree of multiprogramming, and short term scheduler provides less control over the degree of programming. When we talk about time sharing system, the time sharing system is absent in long term scheduler, but time sharing system is the part of the middle term scheduler, and it is also minimum in the time sharing system is also minimum in the short term scheduler. Long term scheduler select the process from the pool and loads them into the memory for execution. Middle term scheduler reintroduce the process into memory as as we can say that as we have said that the middle term scheduler works between the running waiting and the waiting to the ready state. So it reintroduces the process into the memory. And short term scheduler select those processes which are ready to execute. After this, we come about the some key terms related to the concurrency. So the first key term is the critical section. What is this section? Is this section of code is the section of code in which we requires access to share the resources, and they may not be executed while the other process is in the corresponding section of the code. Means if there is one process in the critical section, so though no other process will execute in the critical section. Next is the deadlock, is the situation where no two or more process can execute. Mutual exclusion is the requirement when one process in the critical section that access the shared resources, no other process may be in the critical section that access any of the other shared resources. Next, race condition, it is the situation in which multiple thread or processes read and write the shared item, and final result depend on the relative timing of their execution. And starvation is a situation in which a runnable process is overlooked indefinitely by the scheduler. And live lock is the situation in which two or more processes continuously change their state in the response to the change of the other processes. So first I talk about the race condition. It is an undesirable situation that occurs when the device or system attempt to perform two or more process operations simultaneously, but because of the nature of the device or system, the operations are not executed properly. So a situation arises where processes access the same data concurrently, and the outcome of the execution depend on the particular order in which they are accessed. So this condition is known as the race condition. Next is the critical section. The critical section is the problem in which each process must ask permission to enter into the critical section entry section. This will be clear through this code, which is the general structure for any process. Do entry section, critical section, exit section, remainder section. What this code shows is that we need a permission to enter into the critical section, and if one process is in the critical section, then no other process will enter into the critical section and use any shared resources which are currently used by any of the process which is in the critical section. So the solution of critical section problem is mutual exclusion, in which we state that if the process PI is executing, then no other process can be executing in their critical section. Mutual exclusion means like mutually we decide कि if there is a one process in the execution, then no other process will ask for the shared resources. Another is progress. If no process is executing in its critical section, there exists some processes that wish to enter the critical section, then the selection of the process that will enter the critical section next cannot be postponed indefinitely. Means a process is going on, progress is going on, and there is a solution of critical section. Last solution is bounded waiting, in which a bound must exist on the number of times that other processes are allowed to enter in their critical section, and assume that each process execute at a non-zero speed, and there is no assumption regarding the relative speed of the n processes which are executing. So the critical section handling can be done by the two types, which is preemptive or non-preemptive. Preemptive means allow preemption of process when running in a kernel mode, and non-preemptive means runs until the exists in the kernel mode. Preemptive and non-preemptive, in simple meaning I can say that preemptive means we can switch to the processes by storing their state, and non-preemptive means when the one process enters, it completes, and only after completion it exists from the kernel mode. Okay. So the next is the type of solutions which are software solutions. We have some algorithms whose correctness does not rely on any other assumptions. Hardware solutions rely on some special machine instructions, and operating system solutions which provide some functions and data structures to the programmer to solve these type of problems like critical section, like race condition, like deadlock. So it can be also done through, it can be also solved through these types of solutions, which is provided either by the software, hardware and the operating system. So with this, so these solution is provided through some types of algorithms, which is Decker algorithm and Peterson algorithm. So in Decker's algorithm, we use the condition of busy waiting. There are two processes P, I and J. If we assign a flag J, if flag I is true, then we execute busy waiting of flag J, and if flag J is true, then we execute the flag I. So in this algorithm, there is a global memory location that both processes could access, and each process examines the value of the turn if it equal to the number of process, and the another is busy waiting, since the process are waiting to get the access to the critical section. So when the flag J is executing, they are waiting to enter in the critical section, and when I is executing, they are waiting entering into the critical section. So next is Peterson algorithm. In this, we have some flag, and by stating the values of the flag, we variables enters into the critical section. Like say there are two process solution, the two process shares two variable turn and flag, and turn by turn indicate whose turn into the enter then the critical section, and the flag array indicates if the process is ready to enter the critical section. The flag I is equal to true implies that the process I, which represents to the variable I, is ready for entering into the critical section. So Peterson algorithm is used to synchronize two processes. It uses two variables, and I represents the consumer and J represents the producer. There is a problem which is producer consumer problem. Okay. So producer consumer problem means that as much we produce, it should also be consumed at the same time. There should not be any overflow of the production. With this, thank you very much, and Jai Hind.